All right, so much of Unit 2 is Newton's laws. Okay, Newton's first law is pretty simple. Okay, Newton's second law takes up 2/3 of the unit. Newton's third law, pretty minor. Okay, and then we go into like work and energy and stuff like that. Okay, for the other part of it, but we need to know all of Newton's 3 laws, or his 3 big laws, because they do determine the motion of objects. Okay, they're very important in the determination and understanding of the motion of objects. So that's why we have to go over them. So we'll start out with the simplest of his laws, and that is his first law. Okay, Newton's first law can be summed up into one word, and that word is inertia. Okay, Newton's first law is absolutely not rocket science. It's part of rocket science, but in and of itself is not rocket science. Okay, Newton's first law says that this desk over here will stay right here, provided nobody touches it. Well, duh, of course it will. Okay, it's pretty common sense that unless you're pushing or pulling on an object, it's going to stay where it is. Okay, but it expands also to apply to something traveling at a constant velocity. Okay? If something is traveling at a constant velocity, it'll continue to do so unless it is acted upon by an external unbalanced force. Okay, so if you're traveling down the highway and you have your cruise control on, you're traveling at a constant velocity, right? All the forces are balanced. That's what your cruise control is always attempting to keep true, right? If you start going up a hill, the cruise control throttles up or gears down or whatever, okay, and allows more force forwards to be applied because there's now more force backwards. Okay, if you're going against a strong wind, okay, then it'll have to throttle up because that's a force backwards, and it'll have to exert more force forwards in order to continue to maintain a balanced force situation. Right? So Newton's first law deals with situations where there is no net force. Okay? Okay? F net means the net force. And net force is the vector sum of all forces. And Newton's first law governs all situations where the net force is 0, where all the forces add up to be totally balanced. Okay, so this desk here is a very simple Newton's first law example. There are 2 forces acting on this desk right now. What are they? Gravity is one of them. The other one is less obvious. What would if only gravity was acting on the desk, what would it be doing? Right, falling, accelerating downwards, all right? It's not. What's keeping it from doing that? The ground, exactly. Okay? The ground exerts something that we call a normal force, okay? Or sometimes restoring. Most of the time we call it normal force, okay? And that is that it is exerting a force upwards that balances gravity. And as a result, the net force on the desk is 0. If I sit on the desk, does that change anything? It doesn't change the end result, okay? If I sit on the desk, it doesn't change the end result. All it changes is that gravity is now like 800 newtons greater because I'm sitting on it and I'm big, okay? But now the floor also has to push. Yeah, it's got to push harder, right? Because now I'm sitting on the desk, so now the floor's got to push harder, right? I mean, if you're just laying on the ground, you don't feel too bad. Somebody comes along and stands on your chest, you feel a lot different because now you're exerting a much greater force because more force is being exerted on you. Okay? The end result is the net force on you is still 0. Okay? But you have to exert more force upwards in order to balance that person. Okay? So Newton's first law governs all situations where the net force is 0. There aren't very many situations where the net force is truly 0. Okay? It's very difficult to have that, except maybe in outer space. Okay? In fact, in outer space, Newton's first law is a real problem. Because once you get moving in space, In order to stop, you have to exert a force in the opposite direction. Not something we ever think about on Earth. Okay? Because between the forces of gravity and friction on Earth, we know everything will eventually come to a stop. In space, not the case. Okay? If I get something moving and it runs out of fuel, it's just going to float away because there's nothing you can do. Right? You can flail your arms in your spacesuit and scream and holler all you want, but it isn't going to do you any good because you can't exert a force in space by flailing. Right? You will just continue to move forwards, okay, until you are encountering another force, which in space could be a very long time. You'd probably be out of oxygen and food and all that other stuff. Okay, so you don't want that situation. So you have to be very mindful in space of your fuel situation. Right? We'll watch a video about that in a little bit. Okay. So the other thing we got to understand about Newton's first law is that inertia is related to the mass of an object. The more mass you have, the more inertia you have. Okay, I mean, think about it. If you got like a little kid on a tricycle, okay, you can like push them and they'll go really fast. Okay, if you have a bus and you do that, does the bus move? No, it has way more inertia than the little kid on the tricycle. Okay, it has more of a tendency to continue doing what it was doing. Okay, and that's what inertia is. Okay, the tendency of an object at rest to remain at rest, or the tendency of an object in motion to remain in motion, okay, at a constant velocity. If I want to change the velocity, I have to apply an unbalanced force. That applies to the thing that's sitting still as well. If I want to change its velocity, I have to apply an unbalanced force. The bigger, more massive the object, the more force would be required to change its inertia. Okay. All right, where does this come into play in a real world situation? Yes, in a physics 20 question, yeah, absolutely. All right, I'll give you a situation. You're traveling down the Deerfoot at 120 and there's a car going the wrong way straight toward you. What would you rather be driving, a semi-truck or a smart coffin car? Semi. Okay, you want to be driving the bigger vehicle. Why do you want to drive the bigger vehicle? It has more inertia, right? It's going to take more force to change its velocity. If you're driving the smart car, yeah, I call it a smart coffin because they bury you and the car in the same hole. Okay, it'd be hard to separate the two of you. Right? You don't have much inertia in a smaller vehicle. All right, so when we're talking about safety systems in a car, the obvious ones come to mind. Seatbelts. Seatbelts are by far the most important safety device in your car. They keep you in the car. They defeat Newton's first law. Okay? Newton's first law says that an object in motion remains in motion until affected by an unbalanced force. If you are not wearing your seatbelt, the first unbalanced force to act on you will be, yep, the windshield, and then the road, and whatever else you happen to hit on your way. Okay, seatbelts prevent Newton's first law from killing you. So wear them. They're important. Okay, airbags, similar. They're not going to save you on their own though. Okay, all an airbag really does is help to cushion your head. Okay, it helps to slow down how quickly you slow down. Hope that makes sense. Okay, back in the day before airbags, okay, steering wheels were these hard, sometimes like semi-metallic objects. And when you got in an accident, your head came forward and hit the steering wheel. Okay, you look at anyone from like, well, my generation and a little older, okay, who'd been in a car accident, they all have the same scar right across the hairline right here, because that is where the steering wheel would hit you and peel your scalp back. Okay, it's steering wheels were hard and rigid. Wasn't very smart, but that's the way they were designed. Now, they're designed to collapse when you hit them. They're softer. The steering column will break and move away from you. Okay? In an accident, all things designed to make your acceleration down to zero take longer. The longer that acceleration takes, the better off you're going to be. Okay? The safer you will be. So all the safety devices in a car are designed to make a crash take longer. Okay, I know that seems weird. You think, oh, I just want the crash to be over. Actually, you want it to take as long as possible. The longer it takes, the better off you're going to be. If you're in a smart car, the crash will be over very quickly. and you'll likely be moving backwards, which is also bad. Okay? The car that goes forwards at the end wins. And believe me, in every accident, there's a winner and a loser. Okay? The winner is almost always the more massive vehicle. The only time that would not be true would be if the smaller vehicle was traveling at an unbelievable, almost impossible to reach rate of speed. Okay? Then it might have enough kinetic energy to do enough damage. But most of the time, like 99.9, it is the more massive vehicle that wins. Okay? And you ever been in a car accident? Okay. In 3? Airbag go off in any of them? Okay, so like fender benders, small things, right? Okay. Car accidents that are more serious, okay? Let's say you're going faster than 60 kilometers an hour when they happen, okay? Will usually result in the detonation of your airbag. Okay? Your airbag works on Newton's first law. It has a little sensor, similar to the one that's in your phone that tells it which way it's oriented. It's called the gyro. Okay? When it moves, when you stop rapidly, the gyro continues to move forward because it's suspended on springs. Okay? And it moves forward and it touches a circuit plate, completes the circuit, which detonates the airbag. And if you've ever been in an accident where an airbag has gone off, it's an explosion. Right? There's no better way to describe it. It is an explosion. It blows up in your face. Not a pillow. It actually hurts. Okay? If you're driving, you'll have bruises on your arms where the airbag hits them. Okay? But it's better than hitting the steering wheel. Okay? So anyway, it's on this sensor that uses Newton's first law. The car stops, but the sensor keeps moving forward. Touches the plate and detonates the airbag. Okay? Your seatbelts work on the same principle, okay? In that they save your life by Newton's law, but they're also activated by Newton's first law. Okay? There's a little catch inside of them that's on a pendulum. So when the car stops rapidly, the pendulum moves forward and locks the seatbelt from unraveling. Right? You've all had this happen to you, right? You get in the car and you're in a hurry, and you're pulling on the seatbelt and it's locked, and you can't slow yourself down to let it go back in. You just keep jerking on it. Okay, that's the pendulum has just been jerked into position where the locking bar is now set. Okay, you have to let it retract in order to get out. Right? But all of that stuff, all of it works on Newton's first law because Newton's first law is immutable. Okay, there's nothing you can do that will make it work wrong. Okay, it'll always work correctly. And so we try and make as many things as possible work on Newton's first law. That was the problem actually with early airbags. Early airbags did not use a Newton's first law triggering system. They had a contact sensor in the bumper. Okay? So when if you hit the bumper hard enough, the airbag would detonate. Okay? There's actually a video of an old lady walking across the road, just like really, really slow. And this guy in this like brand new Mercedes convertible is honking at her and angry that she's taking so long to get across, and she finally snaps and hits the front of his car with her purse and detonates his airbag. It's like the most karmic thing ever. Okay? But they don't make airbags that way anymore because obviously it's not an effective way and they can be misfired. Okay? You do not want an airbag to misfire, okay? Especially like while you're driving. Okay? If you're not in an accident, you don't want it to go off. Okay? All right, so those are some of the things that we need to consider, okay, about Newton's first law. Now I'm going to show you, okay, Newton's first law in action here with a video of smart cars. Okay, so we've seen what happens now. Small object like a smart car in a collision, okay, and it gets essentially utterly destroyed. Now, I mean, we're picking on the smart car a little bit. That's not what a smart car was ever designed to do, okay? A smart car was not designed to, cruise down the Deerfoot at 120, okay? They were designed to be in slow-paced, stop-and-go traffic and be efficient on fuel, okay, in those situations. They were never designed to be a freeway driver, right? Just stop-and-go traffic. So, they're designed to withstand a collision at stop-and-go traffic speeds, 60, 70 kilometers an hour, okay? Not much more than that. They were never designed for a high-speed collision because they were never designed to be driven at high speed, okay? Now, we talked about seatbelts are important. Okay, we talked about airbags are important. Okay, the most important safety feature in your car is mass. The more massive you are, the more inertia you have, and the less your change in velocity will be in a collision. It's mass that will save you. Okay, well, not so much save you. It's mass that lets you win. Okay. Okay, I've been in a couple of accidents, one at 60 kilometers an hour. Okay, I had a lady who just turned left I don't know how she didn't see me coming in my big truck, but she did. Okay, turned left right in front of me, and I'm just driving through. Okay, at about 60 kilometers an hour. I had my whole family in the truck. Okay, and she was driving like a little Ford Focus. Okay, so a small little sedan, and we cut through that car like a hot knife through butter. We were just way bigger. Okay, we had way more mass, like easily 3 times the mass of that car. Okay, so when it was all said and done, my bumper had to be replaced, one headlight assembly, and a dent taken out of the driver's side quarter panel. Okay, that was all the dent. My airbags didn't even go off. Okay, because our velocity did not change enough to trigger the airbag sensors. Okay, and yeah, the kids were in the back. They were in their car seats. They were like asleep, and then they woke up. Okay, they weren't hurt at all. Okay, none of us were hurt. You know, didn't get bruises from our seatbelts or anything because the forces that, or the acceleration we experienced was far less than hers. Both of her airbags went off. Okay, we broke the engine mounts. So when we went into the hood of her car, okay, we penetrated far enough that we destroyed the radiator and broke the engine from its mounts. It was actually had to be pulled off of the road. Okay, because we went that far into her car. Okay, mass mattered in that situation. Okay, sure, we had safety devices too, but none of them were necessary because our acceleration wasn't sufficient to trigger them. Okay, her acceleration most definitely was. Okay, the accident started in the middle of the intersection. Okay, the collision was finished on our side of the road, 7 meters past the intersection in the direction I was going. Okay, mass mattered. Okay, mass is what allowed us to win. I like to win. I'm a competitive guy. Okay? Even in a car accident, I want to be the winner. Okay? And it wasn't even my fault because she turned left in front of me. So it was all her fault. It's all good. Okay? But keep that in mind. In an accident, mass matters. If you're driving something small, don't get in an accident. Well, don't get in an accident, period. But if you're in something big, it's less likely to injure you. Okay? All right. So let's look at Newton's first law here. So forces. Force is going to come up all the time. Force is the most important term in Unit 2. Right? So what's a force? A force is a push or a pull. Okay? Anytime you exert push or pull, you are exerting a force on something. Okay? Forces can be of essentially 2 kinds, and I don't mean push or pull. They can be contact forces, which is one of the ones we'll deal with most often, and there are field forces. We will only deal with one field force in Physics 20, and that field force is gravity. Okay, the other field forces are electricity and magnetism. Okay, there's electric fields, magnetic fields. Okay, the Earth also has a gravitational field due to its incredible mass. Okay? So what we're saying about a field force is a field force doesn't have to be in contact with an object to exert a force on it. All right, so a plane flying through the air isn't in contact with the Earth's surface, but gravity still acts on it. All right, contact forces are pushes and pulls. Right? If I'm going to push on something, I have to be either directly or indirectly in contact with it. Right? Either I'm directly pushing on it with my hands, or I've got some other device that I'm using, a lever or something like that, okay, that I'm using to push or pull on the object. Okay, pulling forces, okay, they can be direct. I can directly pull on the object, or I can use a rope, cable, rope. They're all rope. Okay, I can pull on them with the rope. What can I not do with a rope? Push. Yeah. Okay. My old physics teacher from high school used to call that Mr. Hill's first law of physics. You cannot push on a rope. I mean, think about it, right? Tie a rope to something and then go like this. Doesn't work very well. Okay? You cannot push on a rope, so it doesn't work that way. Okay. All right. So, like we said, force is a push or a pull. Okay. Anytime an object is pushing or pulling on another object, a force is being exerted. Okay. Mass is also important. Mass is the amount of matter you possess. Okay. The more matter you possess, the heavier, more massive you will be. Okay. All right. So a penny doesn't have very much mass because it's not made of very much matter. Right. There's not that many atoms or molecules or whatever, okay, in a penny. But in a supertanker, there is a lot of matter and thus a lot more mass. Okay, and mass matters. The more of it you have, the more inertia you have, the less likely you are to change what you are already doing. Okay, okay. Another kind of good example would be if you're like, how many of you have ever curled before? Watched curling, paint drying, curling. Okay. So if you're watching curling, okay, the rocks, they're big and heavy, right? They slide down the ice. They have a lot of inertia. Like you wouldn't want to be standing there and have one hit your feet. Right? It'll take your feet out. It has enough inertia to do that. Whereas if I slid the penny down the ice at you, okay, you wouldn't even notice it. Right? It doesn't have enough inertia to change your inertia. Right? Now, if that ice was perfectly frictionless, would the speed of the rock change at all? No, because there'd be no forces to change its velocity. Okay? It's only because there is friction that curling is actually a sport. Okay? If there was no friction, curling wouldn't, well, maybe it would be more interesting. I don't know, because you'd throw the rock and it would always get to the other end. And if there was somebody standing at the other end, they have to jump out of the way. Okay? But there is friction. Okay? And you can alter the direction of that frictional force and the amount of that frictional force in order to steer the rock. Okay, so if you've ever like learned how to curl, okay, you've got your two turns, you got your in turn and your out turn, okay, and that makes the rock spin different ways and that makes it turn differently. Okay, the people sweeping it can also influence the direction it travels. If they sweep directly in front of it, it'll travel straighter. If they sweep more on one side, there'll be less friction on one side of the rock than the other. And it'll turn in the direction of more friction because it slows down in that direction more. Okay? And so they can actually affect the direction it goes if they really know what they're doing. Right? So all of those things kind of contribute to the skill involved in that sport, but they're all affected essentially by Newton's first law. All right, now mass is a scalar quantity. Okay, nobody says that their mass is 72 kilograms left. Okay, there's just 72 kilograms worth of mass to that person, right? That does not have direction. But here's another place where North American society just gets things wrong. When somebody asks you how much you weigh, give them a dirty look because it's not a polite question, and then tell them what you really weigh. They want to know your mass, but that's not what they ask for. The quickest way to make somebody feel really uncomfortable is to give them the answer they want. Okay? Whenever somebody asks me what I weigh, I tell them how much I weigh. I'm like 820 newtons. And then they go, and then they usually go away, which I'm okay with because I'm not a really social person. Okay? And you shouldn't ask me that question. It's really rude. Right? So I tell them what I weigh. Okay? Weight is the force of gravity acting on your mass. You calculate it by taking your mass in kilograms and multiplying by the acceleration due to gravity, which gives you a force in newtons. It's the force you feel if somebody stands on you. Okay? When they ask you how much you weigh, they really want to know your mass. Don't tell them. Okay? Tell them your weight. It's way more fun. I like messing with people. All right, so mass is a scalar quantity. It would be in kilograms, okay, and it would be representative of the amount of matter possessed by that object. Okay, so weight and mass are two entirely different things. Weight is a force. Okay, weight is the force of gravity pulling on your mass. The more mass you have, the more weight you have. Okay, but if I want to lose weight, I don't have to go on a diet. I don't have to exercise. I just have to go somewhere where gravity is less. If I go to the moon, I'll weigh 1/6 what I weigh here. I won't be any thinner, okay? But I'll weigh less. And in the end, well, that's what you're trying to do. Okay? If I want to put on weight, I'll go somewhere where gravity's stronger. Okay? It's not going to help me bulk up. Well, maybe it would, because I'd have to work harder against gravity then. All right, so weight is the force of gravity pulling on your mass. Weight is a force. Okay, mass is the amount of matter you possess. Make sure you keep them straight because they are definitely two different things. And in North America, we get them mixed up all the time. Okay. All right, this guy here it looks like he's holding up the rock. Is he really holding up the rock? No, it's just one of those spots where a rock got kind of wedged in somewhere, but you can sit there and make it look like you're holding up the rock. Okay. Now, if that rock was really not wedged in there, would he be able to do that? Probably not. The rock has way too much mass. Okay. And gravity pulling on that mass would exert a fair amount of force. and would probably crush him. So I would suggest not doing that. Okay, so understand Newton's first law. We talked about curling already. Hockey's another example. Okay, if a player doesn't hit a stationary puck, it remains at rest on the ice. Of course it does. Nothing's acting on it except gravity and the ice, and they balance. Okay, but if somebody comes along and hits the puck, then it will accelerate. How long will it accelerate? Okay, actually it'll accelerate. Yeah, the whole time friction is acting on it, it'll be accelerating negatively. But how long will it accelerate positively? Right. Only while your stick is exerting a force on it. Okay. This is actually part of sports science. Okay. The design of better equipment. Okay. When I was a kid, hockey sticks were chunks of tree. Okay. They were all made out of wood. Sure, wood was actually wood back then. Okay. It wasn't carbon fiber and graphite and all this other stuff. Okay. Carbon fiber, graphite, those are way better materials to make a hockey stick out of because they're more flexible. As a result, okay, an old stick could exert a force on a puck through this arc because it was only marginally flexible as wood can be. Okay? A carbon fiber stick, because it's flexible, can exert a force over a greater distance. As a result, it accelerates the puck at the same rate a wooden stick would, but for a longer time. Thus, you can hit a puck faster with a composite stick, okay, than you can with a wooden stick. Okay, so that's the kind of design behind it. Now, are there drawbacks? Yeah, composite sticks shatter sometimes, and they always shatter at the most inopportune moment. Okay, like you got a wide open goal. Okay, goalie's been pulled, you need to score, and that's when your stick breaks. Okay, and it explodes and makes you look terrible. Okay, but it's still most of the time going to be a superior material. Okay, simply because you can accelerate it for a longer period. But once it leaves the stick, then it stops accelerating positively and starts decelerating. Okay? In the perfect physical world, if it was just sliding along the ice and the ice was frictionless, it would travel at a constant velocity forever. Okay? If we had an infinite amount of ice, okay? It would just keep traveling and never slow down. Okay. So Newton's first law is stated like this. An object at rest will remain at rest, and an object traveling at a constant speed will continue to do so unless acted upon by a net force. In fact, this shouldn't say speed, this should say velocity, because direction matters here. Okay. Does it take a force to turn? Okay. If I've got that curling rock sliding towards me on the ice, and I just want to kind of push it out of the way, I just want to change its direction, not necessarily stop it, do I still have to push on it? Okay. If I want to turn a corner, what force do I use? Okay. We just had snow and slippery roads. Okay. If you take a corner too fast, what do? You obey Newton's first law, and you continue to travel at a constant velocity, straight. Okay, because there's no what? There's no friction. Friction is the force that allows you to turn. All right, if you're going too fast, there's insufficient friction. You travel in a straight line, the same direction you were going when you slammed on your brakes. And then, of course, you forget all the stuff you learned in driver's ed about get off the brakes so that you can try to steer, okay? And you just press the pedal down harder and continue to go straight, okay? Yeah, we forget all those things. Anyone ever watch Canada's Worst Driver? You should definitely watch Canada's Worst Driver. It's always good for laughs, okay? Because they always make the same mistakes over and over again, okay? Like they just pile on the binders and go straight instead of letting off and turning, okay? But we all do it, okay? When we just panic, right? Because we're going straight and we want to slow down, and brakes are supposed to slow us down, but they don't work if there's no friction. Only Newton's law works, okay? And that's bad in that situation. Okay, in this situation here with the book, okay? If I push to the left with 20 newtons worth of force and friction opposes with 18 newtons to the right, what's the book going to do? Will it travel at a constant velocity, stay put, or accelerate? It'll accelerate. Remember, Newton's first law applies in all situations where the net force is 0, where the forces are balanced. In this case, there is a net force, an unbalanced force of 2 newtons to the left. As a result, that will cause an acceleration to the left. Okay? That's what Newton's second law talks about, is what happens when there is a net force. In this case, there is a net force, so the book accelerates to the left. Okay? In this situation here, okay, if you had a bunch of like poker chips or checkers or something like that, and you put them in a stack and flick one at the bottom of the stack, you should be able to knock the bottom one out, and the stack will just fall. It won't tip. Okay? If you do it right, it won't fall, right? Because there'd be enough inertia in the other chips that just the bottom one would be affected. It's the same idea that a magician uses when he does the trick where he pulls the tablecloth out from the dishes. Okay, you guys ever seen that where they just get there and the dish tablecloth comes out and all the dishes stay put? Okay, now don't try that one at home. If you're going to try it at home, here's a couple of tips. Go to the dollar store and get a bunch of plastic dishes. Okay, and get a like vinyl tablecloth because they're slippery. If you try it with a cotton cloth tablecloth, it will not work. Okay, you will just tip everything over. Right? It works best with the cheap little like picnic table ones that are really slippery. Okay? And the key to doing it right is to pull down. That's the mistake most people make when they try it. They're like, yeah, and they lift it up and they do this, and then it just sends a wave through the tablecloth that tips everything over. Right? If you want to pull that one off, okay, you actually push it kind of down and into the table so that it pulls straight horizontally from underneath the dishes. Okay? But if you have dishes on there that are heavy, okay, their inertia is usually great enough that they'll stay there. Okay? Not always, but usually. Takes a lot of practice and probably a lot of broken dishes, unless you have a lot of plastic dishes. Okay, so net force, guys. Net force is the vector sum of all the forces on an object. I had that written on the first slide, but it's important. That's the definition of net force. Okay, so inertia and mass we already talked about. The more mass you have, the more inertia you have. Okay, so the larger the object, okay, the more likely it is to continue doing what it was already doing. Okay, moving at a constant velocity, okay, or being stationary, whichever. All right, so quantitatively, the inertia of an object is measured by its mass. So the inertia of an object is essentially its mass. Okay, so inertia is the natural tendency of an object to remain at rest or in motion at a constant. That says speed again, but it should say velocity. Okay. Okay. The mass of an object is the quantitative measure of inertia. No, no, she just goes back, right? There's no one to save if he's already dead. Yeah. Yeah. Okay, so beginning of class, I was telling you how the seatbelt worked, okay? How it works on Newton's first law, okay? So very simply, inside of a seatbelt, there's a pendulum, a locking bar, and a ratcheted wheel around which your seatbelt winds, okay? So when it's fully retracted, the seatbelt is wound all around the ratcheted wheel, okay? Your car isn't moving, so the pendulum hangs straight down. Right? You put on your seatbelt, it unwinds just fine. If you get in the car quickly and jerk the seatbelt, then you will make the locking bar rotate down and catch, and that's when it gets hard to put your seatbelt on. Okay? In a crash, according to Newton's first law, the pendulum will swing forward. Okay? Because it's on a hinge, okay, this part of the pendulum will reach up and tip the locking bar into position where it'll catch the ratcheted wheel and prevent it from releasing the seatbelt. Okay, in a crash below 60 kilometers per hour, okay, your seatbelts will be fine. You can use them again. In a in a crash more than 60 kilometers per hour, your seatbelts are actually somewhat elastic. They do stretch. Okay, if they were just perfectly rigid, they'd be quite harmful to you. So they do have a bit of stretch to them. Okay, if you get in an accident, usually more than 60 kilometers an hour, the general rule is if the airbags detonated, the seatbelts are shot. Okay, so they would have to replace the seatbelt if your car was actually still salvageable. Okay, once airbags detonate, the car is usually close to the write-off point because it's expensive to replace airbags, seatbelts, all the body panels and stuff that would be wrecked. So, like we say, the car is designed to sacrifice itself, okay, in a collision. All right, so we'll look at a couple of kind of review activities here that mostly have to do with how we draw diagrams in Unit 2. Okay, so what you see here is what we call a free body diagram. Okay? A free body diagram shows the object in question with all the forces acting from its center, what you would sometimes call the center of gravity. A purist would call it the center of mass, okay, because that's where your inertia is located, at your center of mass. Okay, so if we're looking at a car that has run out of gas and is coasting to a stop, okay, there would be three forces acting on it. This force here, which would be what we called before the normal force, that's the force of the ground, okay, reacting to gravity. And then we have the force of gravity acting straight down. These two forces are equal, so they cancel or balance, okay? They're not really part of it, right? This is the force of friction. We are coasting to a stop, right? So the forces are not 100% balanced. There is this small unbalanced or net force, okay? So what a free body diagram allows us to do is quickly determine if any forces cancel. Okay? If they do, then we don't have to draw them in a vector diagram. And you actually have to draw two diagrams in a physics problem that involves lots of different directions. Okay, because gravity and normal force cancel, I wouldn't include them. Okay, and my only remaining force would be this force, and it would be my net force. Okay, if I had a force that was going, like for example, on your vector assignment in the last unit, you had the two people pushing on the snowball, right? And you had one that was pushing like west and one that was pushing south. Okay, that was the free body diagram. There was this force west and this force south. Once I've identified that those don't cancel, then I draw a vector diagram in order to determine my net force. Force is a vector quantity, okay, and the net force is the vector sum of all the forces involved. Right, so we determine it in the same way that we determine displacement and stuff like that in the last unit. Right, so we would determine theta, we would determine the net force, and then we would go on to use Newton's second law to determine the acceleration of the object. Now, a free body diagram does not actually need to contain a picture of the object. Thankfully, for those of you like me who can't draw, a free body diagram represents any object as a box. Okay, car, cat, skateboard, curling rock, it's a box. Okay, draw it as a box and write the mass inside. So if it was a car, maybe something around 1,500 kilograms. Okay, so it's really easy to draw free body diagrams. All they do is help you to identify all the forces, the direction in which they act, and if any cancel. Okay, but it's essentially, that's how you would write your givens in Unit 2, is with a free body diagram. Okay. All right, questions on what a free body diagram shows us? Everybody okay with those? Okay. All right. That's actually, okay, so try 1 and 2 here. They just want you to draw free body diagrams of these two situations here. So give those a try, see how you do, and then we'll draw them together. Okay, let's just have a look at question 1 here. Okay, so on question 1, we have this car. We know it's 1,019 kilograms, okay, and we're supposed to draw the free body diagram for it. Okay, so the first two forces I would draw in would be gravity. Okay, did they tell me what gravity was? Actually, they did back here. Okay, it's 10,000 newtons. A car with a weight or force of gravity of 10,000 newtons down is coasting on a level road. So that's why I'm doing this, because they didn't tell you that one. Okay, so 10,000 newtons. So how much is the normal force then? 10,000 newtons. Okay, they're still forces. Yeah, they cancel out, but I still put them on my free body diagram. All right, the other two forces are air resistance and friction. Okay, so air resistance would be 2,500 newtons, backwards, they tell me it's backwards, and then I've got the force of friction, okay, which is twice the size of air resistance, 5,000 newtons backwards. Now I have my free body diagram. Okay, from there, I could draw a vector diagram. And if I wanted to make it really, really awful, I could go, all right, 10,000 down, 10,000 up, okay, 2,500 and then 5,000, right, and find my net force that way, but I don't really need to, right? These two cancel each other off, and these two are collinear. Do I need to draw a diagram for collinear vectors? Okay, I can save myself time on something like that. Okay, but that's my free body diagram for that one. All right, so for question number 2, they tell you the weight of the car, it's force of gravity. Okay, I calculated the mass for you. The way I did that is this, guys. The force of gravity is mass times gravity. So that's G is 9.81. So all I did was divide the force of gravity by 9.81. Okay, and I got the mass. So it's 1,223. We'll talk about that tomorrow. Okay, so try the free body diagram for number 2. All right, so we have a car moving at a constant velocity that starts to speed up. The weight of the car is 12,000 newtons down, okay? And we just said that the mass of the car was 1,223 kilograms. So you got 12,000 down, okay? You got 12,000 up, okay? And then you've got air resistance 36 backwards, and you got 7,200 forwards, okay? That would be your free body diagram. All right.